Our final topic in crankshafts and camshafts is going to be camshaft event timing. Okay, so what do I mean? Camshafts are designed, engineered, in fact, to mess with engine performance. So you can, by the design of your camshaft, control your torque and your horsepower. You can control how your engine idles. You can affect the emissions that your engine produces. The way you do that is by messing with the lobes, how you place them, what they look like. So we've already talked about lift before in general engine measurements. So your lift will determine how high your valve will open, either directly off the cam, if it's an overhead cam engine, or via rocker arm and push rods, if it's a cam and block engine. The other thing the design determines is how long the intake and exhaust valves stay open, the duration of each valve opening. And by changing the profile of your cam lobes, you can make that be a slow opening or a snap open, snap close. You can do a bunch of stuff with that. And the design of the camshaft is also going to determine the timing. When are those intake and exhaust valves going to open? Right at top dead center? Maybe a little before? Maybe a little after? That's what timing affects. Okay, so let's look at an engine here. It's not a great picture. What am I looking at? I've got two gears at this side. They're driving a belt. These are cam shafts. So it's an overhead cam, dual overhead cam engine. Down here somewhere, driving those gears, is a crank gear. So crank and cam. So we're going to go a little vintage here and think about a 4-stroke engine. In order to get 4 strokes, what do I need to happen? I need the piston to go up and down twice, right? So that means I need 2 crank rotations. But I only want to get through all of my events one time. So I'm going to have 1 cam rotation. We haven't gotten into gears yet, that's coming, but if you're going to rotate the cam once and the crank twice, that means the cam gear will be twice as big. The diameter will be twice, or it'll have twice as many teeth as the crank gear. One more review here. So just thinking about angles and degrees. When you start the process on your intake stroke, you have a valve that is open. Your intake valve is open. Let's kind of highlight that right here. Okay. Once you get down to the bottom dead center, you are going to start your compression stroke. No valves open. You hit the top of your compression stroke. Then you come to your power stroke, also with the valves closed. After you're done your power stroke, and then you got to get rid of your exhaust gases, you open the exhaust valve. Okay, so as this happens, what is happening with the crankshaft? Well, I know that the camshaft is turning 360 degrees through all the events, but the crankshaft, here we go, 0 to 180, right? That's halfway down, top to bottom. Let me draw a little diagram. 0, 180. And then we're going to go 180 to 360. And I'm talking about crankshaft rotation here, remember. 360 to 540 degrees, or you can think of that as starting at 0 again, going back down to that 180. But we're on the second rotation, so it's like we've gone through 360, we're heading to 540. And then if you want to have 2 full rotations of the crankshaft, you're going to go 540 to 720. And that will take you back up to the top to the end of the exhaust stroke. From that drawing, it makes sense that, when we're at top dead center, we should open exactly at 0 degrees or whatever we're at, we should open an intake valve. Likewise, at bottom dead center, we should close an intake valve, and on another stroke, we should open an exhaust valve, and at top dead center, close an exhaust valve. But we're always trying to get more power, to make our engines more efficient, to make them do more neat things for us. So we tweak the performance. If you advance timing, what that means is you just open the valve early. If you retard timing, you open or close the valve late. Messing around with this is going to change the lift duration, how long the valve is open, how long air can be moving in or out of that engine. So let's mess around with our intake valve. A lot of acronyms coming your way. If you open the intake before top dead center, BTDC, before top dead center. What does that mean? When is it going to open? It's going to open during the exhaust stroke, which sounds a little weird. What will this do for us? It'll create a scavenging effect where the exhaust gases leaving through the also open exhaust valve will pull clean air in through the intake valve. So that'll get more air in faster, which is always the race. You don't need to do this if you have a forced intake engine, but yeah, if you're naturally aspirated, it's a totally awesome thing. What happens if we open the intake valve after top dead center, ATDC? Well, your valve's going to open after the piston's already moving down on the intake stroke. So if the exhaust valve is still open, which is a possibility, you might draw in some exhaust gas by accident, a little bit of a drop in power if you're recirculating exhaust gases. And if the exhaust valve is closed, you're going to have only that oxygen-rich air coming in, but for less time. And if we think about when this is happening, I'm just going to draw a little line there. 0 degrees, 180 degrees, so top dead center, and this is crankshaft rotation, bottom dead center. We're talking about opening the intake a little early. So if it normally opened at 0, that means an early opening might be a line here, a few degrees early. A late opening, 8 TDC, would be a line here, a few degrees after top dead center. We can also mess when we want to close that intake valve. So I'm still only talking about the intake valve. We're going to open it early or late, and we can close it early or late. Okay, so, and that happens at bottom dead center of the crankshaft rotation. So if you close it before BDC, BDC, before bottom dead center, what's going to happen here? You're still going to be in the intake stroke when the valve closes, when the intake valve closes. So is this awesome? No, it's not really going to help your volumetric efficiency. We're always trying to maximize the air you can get in. So you're not usually going to see an intake valve close early. If, however, we close the intake valve after bottom dead center, oops, this should be an A. There we go. A BDC, so watch out for me making mistakes there. Your intake valve will still be open as you start the compression stroke, as a piston starts coming up again. So what can happen then? If you're a clever engineer, you can take into account pressure waves in the intake air system that are going to allow air to continue to enter the cylinder, even though the piston is rising. And then you have to mess with the timing really carefully because you need to balance that pressure wave effect that's going to pull in extra air, even though the piston is rising, with the possibility of forcing the air back out the valve during compression, which is definitely not what you want. And once again, on the side, I'm just going to draw the straight line that represents crankshaft rotation, 0, 180, top dead center, bottom dead center. So if we are thinking about this situation, intake closing before bottom dead center, if it had been planning on closing at 180 and it closes a little early, you're going to get a line like this, a few degrees before bottom dead center. If it is closing after bottom dead center, like I messed up my colors there. You're going to pass through bottom dead center and go a few degrees further. Let's think about the exhaust valve, and first we're going to think about opening it. So opening would normally have an at bottom dead center when the piston's at its lowest point right before you start to rise and push out the exhaust gases. So if you open that exhaust valve early before bottom dead center, it's going to open during the power stroke. What's the problem with that? Well, if your combustion gases haven't fully expanded, you're throwing away power, right? Like you're opening a way out for the pressure before you've fully taken all the power from the piston being driven down. However, if you release some of that pressure prior to the exhaust stroke starting, there's less work required to push that piston back up. There's a less, force on it. So it's a little easier to get rid of the exhaust gases. So once again, it's a balancing thing. What's the best situation? If I open the exhaust valve late after bottom dead center, you're already into the exhaust stroke. So you know that all the power on that power stroke went to the drivetrain. But you do have to get more exhaust out in less time. And once again, going over to our crankshaft rotation visualization, 0 degrees, 180 degrees. Bottom dead center, we know that an exhaust valve opens ideally at bottom dead center, but if we mess with it and we open it before, in the orange, that means it starts opening a few degrees before you get to 180. If you open it after bottom dead center, the line looks like this. You start opening it a few degrees after 180, 186, 192, something like that. Now we're going to go over to top dead center, which is when we would have normally had our exhaust valve closing. And we're going to consider closing it a little bit before top dead center, BTDC. So the engine is still going to be in the exhaust stroke, but the valve is going to close early. So you have a risk that you're going to have some exhaust gas remaining in the cylinder. And if there's exhaust gas left over, that reduces the room for fresh air coming in. So it's not an ideal situation. And if we close the valve after top dead center, after we've rotated through that 360 or whatever, the exhaust valve will be open into the intake stroke. Now, we talked about that before with opening the intake early. You get that scavenging effect that helps draw in intake air when the exhaust exits. And it's going to minimize the internal exhaust gas recirculation. Last little stick drawing. This is the exhaust valve closing happens around top dead center. And once again, I'm going to do the colors right this way. If we close it before, we have a line that represents the closing a little early. If we close it after, we have a line that represents the closing a little late. So what happens when we're opening and closing these things early and late? We can create a situation, usually if we open the intake valve early and we close the exhaust valve late, between the exhaust and the intake stroke, where we have valve overlap. And valve overlap can only happen between the intake and the exhaust stroke. And what it needs to happen is that both valves are open at the same time. So this picture's a little confusing, but we have an engine, and this is a camshaft with a couple of lobes on it, a red exhaust lobe and a blue intake lobe, and we're spinning the engine this way. So if we were spinning the engine clockwise from here, the first point we're going to hit is A. And at A, we see that the exhaust lobe is starting to come off of the base circle. So it's starting to open. So exhaust opens here. And if we follow it along, it's going to be open. Let's get a better color, maybe dark red. It's going to be open this whole time, max open right here, coming down. And once it gets back onto that base circle again, that's when it closes. Exhaust closes. Okay, But before the exhaust closed, as we spun around, we hit point B, which is when the intake was opening. So we had the intake opening at B when we came off the blue base circle, and it's open this entire time until it gets back onto that main circle diameter, and then it's going to close at D. Intake close, and it's busy in there, so I'm not going to do it. So what do we have here? We have a little time of rotation where both of them are open. And that's the valve overlap. On this picture, this is a camshaft, right? So it's going to be in degrees of camshaft, but when we draw it, we're going to draw it on a crankshaft diagram, just to make it confusing. Camshaft events on a crank diagram. So having that overlap, what can it do for you? You're just going to use that scavenging effect to get more air coming in, get more time to get all the exhaust gases out, and that will give you better performance at higher rotations per minute. What you need to be careful of is when you're messing that stuff is that you don't want to have it so you're bringing in fresh air or even fuel and it's just bypassing the combustion chain. We're going straight out the exhaust valve into the exhaust manifold. And because you're improving your performance at high RPM, you're kind of messing with your performance at low RPM, so you can expect that rougher, throaty idle. And the last thing I want to mention before we get into drawing these event diagrams is the camshaft shape affecting the valve overlap. So here we see a Mickey Mouse picture of a camshaft with an exhaust valve here, whoops, and an intake valve, exhaust lobe here and an intake lobe here. Okay, that center line represents the maximum opening, the highest valve lift. And we see that the angle between the two is the lobe separation angle. So if we made, and this is going to be terrible, I'm sorry, a picture where they're much closer together, what you end up getting, and I'm trying to draw, is more valve overlap, which seems counterintuitive, but there's more time that they're both open. And if you spread them out really far, oh my goodness, I'm so sorry, you're going to have less valve overlap. All right, let's abandon that horrible drawing and head to the diagrams. So this is where our sticks are going to come into play. So an event diagram looks like this picture. And it gives us all the information we need to know about event timing without requiring us to be so busy. Okay, so we're seeing exactly the same kind of thing there. This graph is beautiful. It tells you all your information. A little more information tells you your lift and all that. But I mean, for overlap, that information's here. But it's also on this. And the lobe separation angle, the center lines, you can absolutely find from the little stick diagram as well. So let's start drawing them. So I'm going to start by pretending this is my crankshaft gear, or just the crankshaft. So I know that 0 is top dead center. I know that a circle, if you rotate all the way around, is 360. I know that 180 is halfway, that's bottom dead center. Okay. If I was on the intake stroke, I start from, I'm going to put a lot of strokes on here, and then we're going to see that we take some of them off. On my crankshaft, I start at top dead center, and I finish my intake stroke at bottom dead center. At that point, I'm going to start my compression stroke from bottom dead center to top dead center. When I finish my compression stroke, I start my power. Piston goes down top to bottom. Then finally, to expel all the exhaust gases, I have my exhaust stroke. So there's 4 strokes on a crankshaft rotation picture. But when we do an event diagram, we're going to get rid of the power stroke and the compression stroke. So we're only going to show the intake stroke, which will kind of happen as we go. Our rotation will always be clockwise, and we're going to show our exhaust stroke. Okay, so we're dropping power and compression. When we're at top dead center, we're actually going to be between those two strokes. So there will be valve overlap here. But at bottom dead center, there's no interaction because intake goes to compression, which goes to power, which goes to exhaust, right? So even though it looks like something's happening between the intake and exhaust stroke at bottom dead center, it's not. We just took off power and compression. Some diagrams show all four, but you don't need to do that. So let's bring in the math. How do we read these things? We're going to start by looking at things we want to find out. Intake valve duration and exhaust valve duration. How much valve overlap happened? Where's the center line of the intake valve and the exhaust valve? That means at what angle do we get the maximum opening, maximum valve lift? Okay, so let's start with the intake valve. When did my intake valve open? Well, I've got this written over on this side. So I know that line, which I guess I'll highlight, goes from this point to this point. So I see that my intake valve opened here. So that's intake open. It opened early. We should go IO for that. And it was open all the way through the 180, and then it closed late after bottom dead center. So it closed here. The duration just says how many degrees of crankshaft rotation was it open. Well, I have enough information, right? If it opened at 12 degrees before top dead center, it went through 12 degrees. That's a piece. And then I know from 0 to bottom dead center is 180. It went through 180 degrees. That's another piece. And then it went through 29 degrees to get to the closing point. I had to pause and relocate my math there because I wrote it in the wrong place. All right, so intake valve duration is just going to be the sum of these three numbers, and that's 221 degrees. Okay, let's go back and look at our exhaust valve. We're going to make that one green. So the exhaust valve is open. Oops, I made it red apparently. Wherever we are on this side, going from bottom dead center to top dead center. I started early. I went around and I closed late. That is messy. Okay. So here's where I opened it. Opened my exhaust valve. Went around and through and I closed it right here. Okay. So let's think about the duration. If I opened it early, 25 degrees early, I went through 25 degrees. Then I went from my normal bottom dead center to top dead center, which is 180 degrees. So don't be distracted by this. That has to do with the intake valve. You don't need it for the exhaust valve. And then I'm going to do that little itty bit, 4 degrees. Add those three numbers. The exhaust valve duration is 209 degrees. Okay, now let's talk about the valve overlap. I'm going to make that pink. Valve overlap always happens around top dead center, and it's just the sum of this little number here and this number here. So if you open your intake early and you close your exhaust valve late, you'll probably have valve overlap. So when I look at that, I'm going to say I opened my intake at 12 and then I closed my exhaust 4 degrees late. So there were 16 degrees of crank rotation where both valves were open. That is my valve overlap. Clean the picture back up a bit, and now we're going to talk about the center line. Okay, so the max lift or the max valve lift or the max lobe height is when you have a center line. So it makes sense that you're going to take the duration, so the intake valve duration, and you divide it by 2 to find where the maximum is. And that gets me 110.5 degrees. Now that's great, but that's in the middle of the entire yellow. And we like to tell it relative to the diagram. So the center line is 110.5 from starting here, but I want to know the distance from top dead center. What do I have to do to get that correction? I just have to move my 110.5 back 4 degrees. Sorry, back 12 degrees. So I get 110.5, which I got by dividing the duration by 2, but I subtract the 12 degrees, and I get 98.5 degrees. To tell people that you know what you're talking about, you put in after top dead center. That's when we hit the maximum valve lift. Same deal for exhaust. We are going to take the duration, 209, divided by 2, and we get 104.5. That 104.5 is exactly in the center of this big pink swoop. But I want to know, and we're going to keep this relative to top dead center. Okay, so I want it relative to that 0 degrees before, after, whatever. And I know that my exhaust valve closed a little late. So there's my correction again. 104.5 minus those 4 degrees to move it back. And that will take me to 100.5 degrees before top dead center. So those are where those center lines are. One more review. Okay, here we go. Let's start with the duration. So intake duration. When did this valve open? It opened here. And when did it close? It closed here. So the math, 14 degrees from the bottom before top dead center, plus the 180 all the way through, and then plus 24. Should equal 218 degrees. Exhaust duration. Will be our pink. Starts here, goes all the way past top dead center, so we are going to have an overlap again. We're going to get that 20 plus the whole 180 plus the extra 11 degrees. 211 degrees. Valve overlap between intake and exhaust stroke is the 14 plus the 11 equals 25 degrees. Intake center line. Okay, let's take the duration and divide it by 2. 109 degrees, and then shift it. Move it back 14 degrees, and that should give us 95 degrees, and that's after top dead center. Okay, so it's now measuring it from here to the center line, wherever that might be. Exhaust center line is going to be the, where is our duration? 211 divided by 2 equals 105.5 degrees. And we are going to take that 105.5 and we see that we need to pull it back. So it's going to be minus 11 equals 94.5 degrees. And this time we're measuring it here, so that's before top dead center. What about drawing our own camshaft diagram, which I totally want you to do? You're lucky because you don't need to have a protractor, which you would have to in class, but you can always use a protractor if you want to, but you can just sketch it for me because of the remote teaching. All right, so let's look at our intake valve. It's going to open 5 degrees after top dead center. Interesting. That's a little different. So I'm going to label it here. 5 degrees after top dead center. And when is it going to close? 29 degrees, so I'll make it bigger, after bottom dead center. And then I draw my little arrow to recognize that this is when the intake is open. Now let's go to our exhaust valve. It is going to open 44 degrees before bottom dead center. So if bottom dead center is here, if I want to go 44 degrees before that happened, I have to remember, because our rotation is always clockwise, I have to spin backwards counterclockwise 44 degrees. Likewise, it's going to close, oh, it's also closing before top dead center, so a little different again. It closes here. And it's very important to put the lines on, because it shows you something. This diagram's a little different than our last one. Our exhaust closed, and then some time passed, and our intake opened. So there is no overlap in this engine. Okay, so if you end up with a situation like this where you don't have two lines in this area, then you have no overlap. Let's do it all. Top dead center, bottom dead center. We are going to open the intake valve 6 degrees before top dead center. We are going to close it 26 degrees after bottom dead center. There's the duration of the intake valve. We'll figure that out in a sec. We are going to open our exhaust valve 40 degrees before bottom dead center. And we are going to close it, not to scale, 2 degrees after top dead center. So just paying attention to what letters you see there. So here's our exhaust valve. Opens early, closes late. Intake duration. Opened 6 degrees before, stayed open for 180 degrees, and then closed 26 degrees late, and that is going to give me 212 degrees. Okay, exhaust duration. Opened 40 degrees before bottom dead center, stayed open for that entire bottom to top, and then closed a little late. 222 degrees. Valve overlap, 2 lines in this little slice of pie, which means for 8 degrees, 6 plus 2 of crank rotation, we had both valves open. Intake center line, 212 divided by 2 equals 106. We need to pull it back that 6 degrees so it lines up relative to our diagram. So we minus 6 and we go 100 degrees relative to top dead center, which is after top dead center. Our exhaust center line is 222 divided by 2 equals 111 degrees. And we're going to take 111 degrees and we are going to subtract the 2 to pull it back and put it relative to top dead center, which is going to give me 109 degrees before top dead center. That's it, that's all.